and welcome to the Big Bang. Let's jump into some kinetics, exploring linear momentum and Newton's second law. Picture a mass moving along a path with a velocity v. Its linear momentum would be a vector in the same direction as v, but scaled by the mass, m. So the linear momentum equals m times v. Let's pause on that for now and think of a mass experiencing two forces, F1 and F2. The effect of these two forces will add up and can be represented by a resulting force equal to m times a, where a is the acceleration. You should remember now that a equals dv over dt. Let's replace a with that in our resultant force expression. So now we have F1 plus F2 equals m times a, which now equals m times dv over dt. We know that the left-hand side is sigma f and that the right-hand side can be written as dmv dt. Since m is a scalar, it can be moved into the derivative. We are familiar with the left part being Newton's second law, but let's put the ends together. If mv is a linear momentum, the sum of all forces actually equals the rate of change of linear momentum. The right-hand side can be thought of as representing inertial forces that are balancing the external forces on the left-hand side. Let's explore the idea of inertial forces now. If we have a mass, the same one from before actually, experiencing F1 and F2, the inertial force would actually be going to the opposite direction from the resultant force we would normally draw. This is really just a matter of subtracting ma from both sides of Newton's second law equality. We do that to have the expression equal to 0, and it gives us an understanding that if there is a resultant external force, we have this inertial force that balances it out. Just like we had normal and tangent components for the acceleration, we have normal and tangent components for the forces. This should make intuitive sense since the forces themselves are mass times the acceleration. To get the normal force, we take the mass times the normal acceleration and replace an with the expression for the normal acceleration, which is the absolute value of v squared over rho, the radius of the path curvature. Then, to get the tangential force, we take the mass times the tangent acceleration, and we replace at with the expression for the tangent acceleration, which is dv dt, where we consider the absolute value of v. We'll stop right here, and I will see you next time.